for it to start. Oh, sounds like somebody else just dinged in. Nope. All right, so you should have already accessed the opener. I've been mentioning this. Some classes we talked more about it than others yesterday. Read this. Find my clicker. This wants to know. Now it's no longer think. It's no. So in which direction can we travel through time? Your options should be on your Chromebooks and not on your phone. Which direction can we travel in time? Your options are both forward and backwards, forwards. Only one of them is correct.
Oh, you can only go forward.
You can only go forwards in time. Why?
Because it's just like a good value.
We know that we can see the past. We see the past all the time. Don't stare at the sun, but that's 8.5 minutes ago. Certain stars are further than others. The closest to us that we can see is 4.4 light years away, which is in the Centauri system. You can't see the closest star because it's not bright enough. It's 4.2 light years away. So how would we travel forward? What would we have to do? That's exactly right. We would have to go fast. Does it have to be in space? No. Theoretically, you could get on a bullet train as long as a cow doesn't step in front of the train or anything. You could theoretically go extremely fast around the Earth, and you would actually age slower than the people that aren't traveling fast.
Wait, so whenever you got off, it's still age?
Well, you would age like normal from your point of view, but let's say you had a perfectly identical twin, depending on how much of a stretch there is. If you go fast enough, when you get off the train, your twin is like 20 years older, and you're like a few hours older. That's what we're going to try to. So I'm going to try to explain how this works to you guys today, and that's one of the last things that I do have. Does anybody need a paper version of this? Because that's what I'm going to show you how to do that with the rocket question.
No, I can't view the opener.
Yeah.
You can't view the opener. I wonder if I have the wrong date on it. Let me check.
No, it's
No,
not.
it's the right date. It doesn't have a
Right,
submit
I
button.
Oh, it doesn't have a submit button. All right, let me fix it. It's what happens when we're told to get something done by 8 a.m. and let me fix it. Not the notes, the opener. Let me edit it. Yep, I didn't tell it to do an online submission. Let's see. So online, text, save. You should be able to refresh it now. Like now that it just, and it should give you the text box. I apologize. All right, back to the next one. This should not take us long. I know when I went through this yesterday after school, and there weren't any students in here to ask me questions, and I talk fast anyways, but I got through it fairly quickly. I don't have to go that fast with this, but you should have more than enough time to be able to do the assignment. We were told that our grades had to be in by 8 a.m. I went back and I double checked. If you hadn't done the one on black holes, I had to put it a missing in your portal, but I'll go back and fix it because you have time to finish it. I guess if you go back and do it. We just sort of were, I think we were told at like 10 o'clock yesterday, oh, by the way, because we might be changing schedules on students, all of your grades have to be updated by 8 a.m. And we all went, oh, thank you. That's so nice. I'll wait and give you guys just a second to type in your response. They should all still be on one big chain. Everything should be in one giant chain. I mean, it's like 200 slides long total. It's huge. So the one with the constellations started on slide, and that's way back. Started on slide 67 was constellations. This one is on, back to where it's left off. This one starts on 126. But yeah, I just figured it would be easier for those of you that get it, just to keep it in one huge long chain until we start up another unit. And that way I don't have to keep, reminding myself to send you guys a new link. Let me double check my online. Who else showed up? Okay, I see more people. All right, did I give you all enough time? That's not enough for you to check out your response. I'm gonna take that as a yes. I see Caitlin. Okay, so I see Braylon, Cameron, Caitlin, Sarah, and Taylor. All right, so this whole concept, relativity, was fabricated by Albert Einstein in 1905. The theory of special relativity. And you should have heard this equation before, E equals mc squared. And what it means is that as an object, a material particle that has mass, approaches the speed of light, it's actually converted into pure energy. Which, the opposite of that happens with the Big Bang. Things were moving faster than the speed of light. Nothing was moving faster than the speed of light. It slowed down, and material particles started to form. I don't remember what year Einstein came to the United States from Germany. We had a lot of Germans that left early Hitler days, before things went crazy. If Oppenheimer wouldn't have come over, Hitler would have had the atomic bomb instead of us. They knew that he was not a good individual and what would have happened. And ironically, we're the only country that's actually used the atomic bomb twice on the same country. Other countries have used nuclear warheads, but not that. So here's theory. And now we're not really going to go too hard into math. I will show you some of the baby formulas for like time dilation and stretch. But basically, as things go faster towards the speed of light, their time must slow down. And if you actually approach the speed of light, and once you cross that barrier, just like if you cross the event horizon, time is supposed to stop. We just don't have the ability to test that. You know, the closest black hole to us, and I don't remember its name, I have to look it up, is over 3,000 light years away. It's not the one in the center of our galaxy. That one's 25,000 light years away. But they're all over the place. Anybody's still in this one? So things that are made of matter, like us, solid, liquid, gas, plasma, things that are actually made of stuff, that actually have atoms that compose of them, cannot reach the speed of light. We can't even get remotely close to it as human beings because we're too squishy. The only thing that can reach the speed of light are light particles. Yes. Yes. What's going to be extremely important with today is knowing your frame of reference or your point of view, because that is going to determine how you're understanding your motion. Because everybody's space-time is unique. Well, right now, we're pretty much sharing the exact same space-time. I have to cheat and look at my stuff because I don't keep all the numbers straight. Right now, we're all moving at 460 meters per second. Why? Because we're still, how are we moving 460 meters per second? Because we're on Earth. What is the Earth doing? The first thing, that number I just gave you, is it's spinning. But what else is the Earth doing? Rotating is the spin, the revolution. So going around the sun, it's 30 kilometers per second. Yes. Yes. And what is our sun doing? Well, it is spinning, but is it just spinning in place? No, what is it going around? The black hole. Okay, so, huh?
The sun is?
Yes.
I thought that was our whole solar system.
Well, we go with the sun. We go where it goes. It's our gravitational center. So there's a speed for that. And then we know that the galaxies are all in motion, and there's a speed for that. But we also know how fast we're going with what's called the cosmic background radiation, or CBR for short. So it really depends on how I ask you the question, because ask you how fast you're moving, you're like, I'm not, I'm sitting here. Well, it's not necessarily a true statement. Depends on how you're looking at it. And those numbers that I just said, they're built into the nets. Okay, so go back to when we first started this, back in the Ptolemy days. Their frame of reference, their point of view was everything went around the Earth. It didn't look like their geocentric model. It looked like it was. The sun comes up in the same spot, sets in the same spot, and then comes up behind it, sets in the same spot. Stars look like they go around us. Oh, I got a message on my phone. But we know that that's not true now. We know that things go around our star. We also know that our star is in motion around the black hole. We also know that our whole galaxy is spinning. We know that it's going towards the spot. They call it the Great Attractor. All of the galaxies are migrating towards this point. You don't really know what's there, but they're all heading towards this point at a certain speed, which is why we're going to crisscross paths with Andromeda. And it's going to eat us. Because its black hole is like 30 times the size of ours, and bigger things win in space.
So we're all going to die.
Oh, we're all going to die, I guarantee you, 100%. Everybody in this room is going to die. Hopefully a very long time from now.
Is that a threat?
No, it's not a threat. From Andromeda in 4 billion years, it's going to come eat you. There's not anything we can do about it, but you know, like I said, at the same time, in 4 billion years, our sun is going to red giant and eat us anyway. So, I mean, we got 4 billion years to figure it out. But you and I will not be here in 4 billion years.
Don't say you never know. Probably.
You're going to upload your consciousness into a computer program and live forever.
Steve Harvey did it.
You're going to harvest other people's organs. That's a little disturbing. Oh, I think there was another one on here. Hold on, let me get back. Looked like something else popped up. Yeah, so like I said, it does depend on what your point of view is. And I have a couple ways that I can actually help you understand this. So those numbers I was throwing at you, this is the only one that's in meters per second. All the other ones are in kilometers per second. If I change this to kilometers per second, it would be 0.460 kilometers per second. That's the equivalent of it. So, yeah, the Earth is spinning at 460 meters per second. So we're all traveling that together. The whole planet is traveling that together. The sun, the motion of us going around the sun is at 30 kilometers per second. So you would be adding all of these things together. So we got 0.46 kilometers per second of the spin of the Earth. We've got 30 kilometers per second of the revolution, which is going around the sun. Our entire galaxy is spinning at 220 kilometers per second. So we have that motion going on as well. That point that I say that we're heading towards, that they call the Great Attractor, the speed's been calculated to be going at 1,000 kilometers per second. Now, if I ask you in relationship to what is called the cosmic background radiation, which is what CBR stands for short, cosmic background radiation, we have a different speed. Now, and that's as far out as we can see. That's the edge of the observable universe. In relationship to that boundary, we're moving at 390 kilometers per second. So it depends. How do I ask you? How fast are you moving? It's in relationship to what?
Yeah, Earth's spinning.
Well, but we're doing all of this simultaneously.
Mm-hmm.
All of this is happening simultaneously.
Now
Now you don't feel whatever the heck this adds up to. You don't feel like you're going that fast
This is gravity.
because of the gravitational pull of the Earth. That's right. We're stuck here. We evolved this way.
What if you jump really, really high?
You mean like that? No. Now, there's a lot of people that ask what happens if all of a sudden the Earth put on brakes and just stopped spinning.
Oh, we'd go.
Like our bones would be torn out of reflection.
We would go. I've seen this video
On what if?
Yeah, we would just.
You would not survive if the Earth just put on brakes. We would basically
It's like
yeah. If Let's just hope the Earth doesn't decide to stop. All right, so let me make this a little bit easier. So you're on a train, or you're on something that's moving. In this case, we're on a train. The train is in motion. And you're going to walk from the front to the back, and you're walking, just taking a nice slow pace at 3 miles per hour. So you feel like you're walking at 3 miles per hour because you are on the moving train. You are moving with the moving train, just like we're moving with the spinning Earth. So when we walk, we feel that we're only going a certain speed. But from somebody looking from the outside, they're going to see a combination of these speeds. So if you have somebody outside and the train comes whipping past and the train's going 60 miles per hour and you're walking an additional 3 miles per hour, depending on which direction you're walking, you might subtract if they're going the other way, but we're not going to do vectors in here, that's physics. In this case, you would add the two and you're actually moving at 63 miles per hour from the person outside the train. That's their point of view, that's their frame of reference. Yours, you're only moving at 3. You're literally adding. Same thing on a plane. The planes go a lot faster. Because you're moving with the plane, I mean, you feel the takeoff and you feel when you stop, you feel that acceleration and deceleration. But when that plane is actually going, I don't even know what they travel, 300 miles per hour? I don't know what the average speed of an airplane is. I'd have to look it up. But you're moving with it. So your speed is the combination of your personal speed plus the craft speed. All right, now, we've already said that we're made of particles, so we can't go the speed of light. Maybe we can't even remotely approach the speed of light, which is called a relativistic speed. Only light can go the speed of light. Only nothing can go faster than the speed of light. At least that's the theory behind the Big Bang, and that's how things rematerialize. The travelers have a different time than the people that are left behind. And yes, Interstellar did get that right, and they showed it very well in that movie. But everybody's space-time is dependent on whatever their personal situation is. Everybody has their own space-time. Even when I'm walking back and forth, because I'm moving a teeny tiny bit faster than you, according to the theory of relativity, I'm actually aging a little bit slower than you are. But when you put in relationship of the speed of the planet, and then the motion around the sun, and then the motion of that around the black hole, and then the motion of that hurtling towards that point in space that's called the great attractor, there's my little motion back and forth means nothing. Now, the person that is left behind is always going to age faster than the people who leave. Whether it's somebody goes into space, so we are left behind, the person in space is the traveler, they age slower in relationship to us aging faster. You saw the movie Interstellar when they were at that water world. No, I'm not ruining the movie if you haven't seen it. But when they left their ship and they went down to that planet, the guy that was left in the ship was a person that was left behind. And when the people that were down on the planet, they were stuck there longer than they wanted to be. And when they came back, that guy aged like 30 years and they were down there for like 6 hours. I'm sure I don't have my time exactly right there, but that was portrayed correctly. So you're planet bound, or it doesn't have to necessarily be planet bound because it wasn't that way in the movie. It was the guy that was left behind on the ship. He was the left behind guy. He aged faster in relationship to the travelers. And that's the way that it always works. Our satellites are doing this right now in space. They're on a different clock than we are. They have to be traveling faster than us, or they would be pulled into the gravitational pull of our planet and they would be destroyed in our atmosphere. These things that I still see glowing in people's faces, boys, these things, they talk to satellites in space. So the phone is on our time, but the satellite it talks to is on its space time. Let's see, let me make sure I'm going to say this right so I don't say it the wrong way. They're aging slower So their clocks must be programmed faster to compensate. It's not by much. It's like by a second or fractions of a second, but it does happen. And we have to compensate for that when we put things in space, depending on how quickly they're moving, their clocks are different. All right, this is the kind of stuff that we are not going to do. There are many different equations that are out there. This is just sort of like baby calculus. But these are three of the base formulas that Hawking used, and actually Schwarzschild used as well, to try to figure some of this stuff out. But don't worry, I'm not going to make you do limits and stuff like that. We're not going to do that. Don't worry about that. So in general, the faster the traveler goes, the more stretched the time difference will become. I'm going to teach you how to calculate that just using simple addition and multiplication. Then in one case, division. It's not anything like the previous slides. You have to know a couple things. You need to know the length of the journey, and I need to give you the stretch for the time. And so one way is a whole number, and then the other way is its inverse or its fraction. We can only go forward in time. Like I said, we can see the past, and we see the past all the time. We do it every day. Oh, okay, so the theoretical stuff. So let's say we find out that we've got aliens coming towards us and they're not the good type. And let's just pretend we have the ability to go get into our spaceship that's in our garage and leave the planet. So we're like, oh no, this isn't good. So we decided to go out and take a tour around Saturn and view the rings. We're gone. Depending on our speed, maybe we're gone for like 6 months. Go and tour the solar system, and we come back, and because we were traveling so fast, 500 years passed. When we come back, the aliens are gone. They died out for whatever reason. Not people left, but we're still there. Or maybe they're not. Maybe they're still there, and we're like, oh no. And so we go back out, we do another tour, and we come back another 6 months later. 500 more years have passed, and everything's okay again. We can actually jump into the future. We just don't have the craft to be able to do it like that yet. So problems with this, problems with being able to take vacations to the future. Now you can't come back. You can't come back to now. You can go back to the same place, but you can't come back to that time. So there's a problem with our propulsion. We just can't go fast enough. We are working on it. A lot of satellites use ion propulsion now. They don't even use the nuclear fuel. That's sort of like old technology. Or they actually use solar wind. They actually use the power of the sun, like a giant sail. And it's not wind, it's radiation, and actually pushes it like a sailboat, just not without wind. We don't have force fields yet. Yes. Sure. We don't have a way to protect us. Because if we're traveling close to the speed of light and we come across a debris field, what's going to happen to our craft? It's going to get torn apart. So we don't have the propulsion system to be able to do this. We haven't invented force fields yet. We don't have a way to protect our craft, to deflect things in case we are coming towards them. And if you punch a hole in your craft, even with the tiniest particles, you're going to be sucked out through that hole. You've ever seen like sci-fi movies and stuff where that happens? Or it's happened in planes where the windows are popped out and like people get sucked out the little window, that little teeny tiny window. It's like this big. So we don't have the ability to do this yet. All right, so maybe in the future, it's probably not going to happen in my lifetime. We're just now getting to the point where we're going to be able to take people up into space for fun. It's going to be extremely expensive. I think the Russians are charging like $3 million to go up with their stuff. Yes, you have to be in decent shape, and there's other things you have to be able to do, but they're actually like charging people like for a ticket. Then with SpaceX, we're changing all these different rockets that come and land back down, these reusable rockets that they're doing. So this stuff is changing. I don't know, maybe in my lifetime. Okay, this is what I'm hoping is going to animate the right way. You guys have this in your document. Okay, so you need to know a couple things. You need to know the length of the trip. You need to know how often the beacon or the signal is being emitted. And you have to know your stretch. Okay, so what I didn't put up here is I need to know that the trip that the rocket goes out and back is a total of 2 hours. It's 1 hour each way. It's like the old Gilligan song. But was that a 3-hour tour? I think it was a 3-hour tour. So the rocket is the one that's emitting the flash. The rocket is emitting one every 6 minutes from their clock, not Earth's clock, from their clock. Because we already know that this guy's clock is going to be different. You have to know the length, 1 hour each way, total of 2 hours, which is a total of 120 minutes, 60 minutes out, 60 minutes back. If it sends a flash every 6 minutes, and there's 60 minutes in an hour, it's 10 flashes each direction. That is how I got that. Have I lost anybody yet? Because I haven't even done any of them. The stretch is a value of 2. Okay, so you're going to see that the flashes will take twice as long going out from the rocket to be viewed from Earth, and then inverse it, and it's going to take half the time coming back. If the stretch was 5, it would be 5 times longer out, and it would be a fifth the time coming back. If the stretch was 10, it would be 10 and then a 10. They're always opposites of each other. So on Earth, if going away, the stretch is 2, it's not going to see 1. It's going to see, let's see, we got 10 out and 10 back. I always have to double check myself and make sure that I'm not messing this up. So it's twice the time. So it's going to see 1 every 12 minutes, but it's still going to see 10 flashes, which is already 2 hours worth, 120 minutes. Coming back, it's still going to see 10 flashes, but it's half of that time. So instead of 6 minutes, it's 3 minutes. So the total amount of time it's going to take Earth to see all 20 flashes is going to end up being 2.5 hours worth of time. So that means that the people on the rocket ship are going to age 30 minutes less than the people on Earth. Or you could say that the people on Earth, that the people on Earth are going to age 30 minutes more than the people on the rocket. I'm going to show this from the other perspective. Instead of the rocket giving the flashes, we're going to do Earth giving the flashes. It's still going to be a 2-hour trip. It's still going to have a stretch of 2. We're just going to have the flash, or it may not be like a light. It just could be a radio signal, something that can be able to travel at the speed of light to make this work. And yes, light travels at the speed of light, and so do all the other parts of the spectrum, which would include like a radio signal. Okay, so the other direction. Let's say the Earth is now sending the flashes every 6 minutes instead of the rocket. Rocket's still going for 2 hours. We still have a stretch of 2. So it's twice as long as the rocket's going out to see the flash from Earth, so that's going to be 12 minutes for time. Going back, it's going to see it half the amount of time, which is 3 minutes instead of 6. So we're going to, each way, 1 hour, which is 60 minutes. Going away, it's only going to see 5 flashes. Coming back, come on, divide by 3, is going to see 20. So the rocket is going to see 25 flashes from Earth, or signals, however the heck it is that I word it. So you're going to have a total of 25 flashes in 2 hours. All we have to do is apply the 25 flashes to Earth's time. 6 minutes for each flash, for 25 flashes, multiplies out to 150 minutes, which is still 2.5 hours. So it doesn't matter if it's from the Earth or if it's from the rocket, you still have that same 30-minute difference. The bigger the value of the stretch, the more difference in time is actually going to occur. I know, I can try to teach this to you guys with calculus, I don't want to. Not when I can actually convert it into just simple math, multiplying and dividing. Now I don't think I'm going to ask you to actually calculate the time, and I don't do that in the assignment. I may ask you to tell me something about the difference in the stretch. And like I said, if the stretch is 10, it's going to be 10 times longer going away, and it's going to be a tenth of whatever the value is that I gave you coming back. I'm going to stop recording this. We can get into the meat. I need to